I've written a word problem here to describe this motion. We have a ball launched from a 15-meter cliff at 20 meters per second with an angle 30 degrees to the ground. And we want to find the time of the ball's flight and the horizontal range. Let's first highlight the important things from here. We have a 15-meter cliff, an initial velocity of 20 meters per second, and an angle 30 degrees to the ground. And we want to find the time of flight and the horizontal range. So first we have our delta y. That is the height of the cliff, delta y. We have an initial velocity, so I'm going to draw a velocity vector and label it initial velocity. We have an angle theta, and then we want the delta x, so that's how far the ball travels. But you can see now what exactly we're looking for. Let's first zoom in on this picture here and break the velocity vector into two components. You can skip ahead if you've already seen this, but I'm going to break this velocity vector into its two components. In blue, we'll have the horizontal velocity vector, and in red, we'll do vertical. I'll define the red vertical velocity vector as Vy. This is equal to initial velocity times sine of theta. We use sine because it is the opposite side from our angle theta. For the horizontal vector, we'll do Vx equals Vi cosine of theta. Plugging in our variables, Vx equals 20 cosine of 30, which roughly equals 17.3 meters per second. For our vertical velocity vector, we have Vy equals 20 sine of 30, which equals 10 meters per second. Going back to the initial problem now, I've separated our two variables into red for our y variables and blue for our x variables. And time I've left just in its neutral color. One other thing to notice, I've added a negative sign here to our change in y. This means that I'm going to define up to be the positive direction, as has been standard for the previous videos. There's one other piece of information we need before we start to solve, and that is our acceleration. Since this is a projectile motion problem, the acceleration in the y direction is just going to be negative 9.8 meters per second squared. In the x direction, since there are no forces acting on the ball throughout its flight, we have acceleration in the x direction equals 0 meters per second squared. Now that we have everything together, we can solve. Looking at the y variables first, we have velocity in the y direction, change in the y direction, and acceleration in the y direction. And we're missing time. The kinematic equation that we can use for this is delta y is equal to initial velocity in the y direction times time plus 1/2 acceleration times time squared. Plugging in all of our variables, we have negative 15 equals 10t minus 1/2 9.8 t squared. The minus sign right here coming from the negative 9.8 meters per second squared. We can rearrange this so that it's in the form of a quadratic formula. Negative 1/2 9.8 t squared plus 10t plus 15 equals 0. And all I'm doing there is I'm moving the 15 to the other side. I'm going to simplify our a variable here to be negative 4.9. And then we can plug everything into the quadratic formula. I've set up and solved the quadratic formula here. And I have our two solutions. Negative 1, which is the answer you get if you use positive in the quadratic formula, and positive 3.04, which is the answer when you use the minus sign instead. The answer we want, since we're solving for time, is the positive value. So t is equal to positive 3.04. Now that we've solved for time, we can use it along with these variables to solve for delta x. The equation for displacement is still delta x equals velocity in the x direction times time plus 1/2 acceleration in the x direction times time squared. Note, however, that our acceleration in the x direction is 0, and so this term cancels out completely, leaving us with delta x equals velocity in the x direction times time. Plugging in our variables, this is 17.3 times 3.04, which equals roughly 52.6 meters. To recap, our overall strategy for projectile motion hasn't changed. The only thing that changed in this video is that we had some initial height as well to add to the problem. We still draw the problem out, listing all of our variables, then we split our velocity vector into two components, and finally we solve. Next time, we'll learn how to solve projectile motion by working backwards to find the launch angle or initial velocity needed to hit a specific target. And if you found this video helpful, consider subscribing, and let me know in the comments below what AP Physics topic you'd like to see next. Thanks for watching, and I'll see you in the next lesson.